Welcome everyone to Pure Virtual C++ 2022. This is the third year we have ran this conference. Started off wanted to make a conference for C++, which is all free, all online, which you can watch the content of after and that anyone can come along to. So what we have today is 5 sessions on a broad variety of topics. They're going to be streamed on a bunch of different places. They're on Learn TV, they're on Twitch, we're on YouTube. But if you do want to ask questions to the speakers, I would recommend you hop over to Learn TV, where there's a live chat. Folks will be watching that. Speakers can pick up questions from there and answer them. Note, if you do pop along to Learn TV and want to ask questions, all of that chat is under the Learn TV Code of Conduct. So please do be aware of that. My name is Cy Brand, and I'm going to be your host for today. We're going to be running about 3 hours for the entire conference, just straight through to the end. So there won't be many breaks. Feel free to hop in, hop out, check out what content you want. But please do chat to the speakers. Let us know your thoughts. Now, the first session is going to be presented by myself. I'm going to be talking about what's new in C++ 23. So we can get started on that right away. So if you want to go and look at what is new in C++ 23, you might head over to something like CPP reference and be hit by a page like this, maybe, which is great if you want to see absolutely everything which is available, look at all the papers, see all the documentation, but this is a lot to digest, and there's all of these defect reports. It's maybe not immediately clear to you what is useful for you to apply in your everyday coding, what makes C++ better. So the aim of my talk today is we don't have a whole lot of time, about 30 minutes, so I'm just going to pick a bunch of these which I think are interesting and try to show them in a fun way using my cats. I have 3 cats. One of them is sitting actually right next to me right now, sleeping. I'm sure he will probably join in the conference at some point. We have Marshmallow, Lexical Analysis Cat, and Milkshake. As you may guess, I named the middle one, and the other 2 were named by my kid. So they will probably join the conference at some point, but I'm going to show a bunch of small programs, all involving my cats, which can teach you something about C++ 23. So let's get started. Treats. Now, I don't know about your cats, but my cats all like treats. And they're also a little bit jealous. So if I give one of them a toy or one of them a bit of chicken, then the others are going to want one too. Now, this can be a bit of a problem. Basically, I need to have enough toys, chicken, and catnip for each of my cats. So how am I going to code this? Well, I could take my range of treats, my toy, my cat, my chicken, and my catnip, and I could extend this out like this. So I can have maybe a box full of toys, a box full of chicken, and a box full of catnip. Now, how do I do this transformation, this single range of 3 items into a nested range where each item is triplicated? Well, there's a few different ways I could do this, but let's have a look at using C++ ranges. So let's start with our single dimensional range and then try to turn it into this. It's still single dimensional, but we have taken each element and multiplied it by 3. So one way we could do this is taking our treats and piping it into some custom range adapter. There isn't a range adapter to do exactly this in the standard library, but we could write one of our own and maybe call it myViews repeat range n. So we'd give it 3 to say, take every element and multiply it by 3. So we're still in our single dimensional range. Then we want to chunk up our range into multiple dimensions. And one way we could do that is then taking this result and piping that into stdviews chunk and giving it this size 3 of the chunk. So this is our first new feature in C++23 that we're talking about, std_views chunk. And the thing which you see which has a star next to it in this presentation is a new C++23 feature. There's also a cousin feature. A bunch of these come in like pairs or threes. This comes in pair. We've got chunk and chunk by. Chunk takes a size for the chunks. Chunk by takes some predicate, which is run over your range in order to generate those chunks. But now maybe we want to reuse this. Maybe we have a bunch of places that we want to expand out our range and then chunk it. So maybe we want to give it a name. We'll call it repeat groups. So if we say, take something and pipe it into repeat groups of size n, it's going to expand the range by that size and then chunk it by that range, by that size. How could we do this? Well, we could create our own range adapter. We could do this completely by hand, or we could just compose existing ones. So like we just showed, we could use our repeat range n and our chunk. So here our repeat groups is just a closure object, which calls repeat range n and then chunk. Note, there's no range here. We're not piping a range into these things. We're just composing them so that they can be used later. We're creating our own range adapter object out of existing ones. Now, I don't quite have time to show you how to write this in the implementation of repeat range n because it's quite complex. Note that this is a new feature in C++23, being able to compose our custom ranges with the standard library ones. If you do want to see an example, you can go check out that Godbot link. Then maybe we take this and we look at the assembly output and we realize for some reason this is not getting inlined. I don't know. We could put an attribute on the lambda. In C++23, you can now do this, put an attribute on a lambda. Maybe a contrived example, but this is just to show you this is now something which you can do. This is especially useful if you have additional tooling which looks at attributes on functions and does a static analysis or some additional work. You can now decorate your lambdas with these. Okay, so let's take a little bit of a step back. We've thought about how we're going to split up these treats. But then maybe we do a bunch of work with our cats. They're not so jealous anymore. We can just, give one of them a toy, one of them chicken, one of them catnip. Well, one thing we could do is just allocate each of these to a cat. So we can take our vector of treats and we can take our vector of cats, just marshmallow, milkshake, and lexical cat. And then we just want to match these up. We want to zip them. So we can use the new range adapter in C++23, zip. This just takes our cat range, our treats range, and matches up each element, and will give you back a pair like this. So we would get a pair of marshmallow and toy, pair of milkshake, cat, chicken, lexical cat, catnip. Of course, you don't have to just have two ranges here. You could pass 3 or 4 or 5 ranges, in which case it wouldn't give you a pair, it would give you a tuple of the size of the number of ranges you pass. There's also a cousin of this called zip transform, which instead of giving you back a pair or a tuple, you will give it a function and it will call that function with that pair or tuple as the arguments, and then each element of the range will be the result of calling that function with those arguments. And this will be done lazily, just like with std transform. So it's not going to zip everything together and call all the functions and collect it up into a range. You just give it cats and treats and a function, and every time you ask it for a new value, it's going to call the given function on the next pair and give you the result. So this is done lazily. But maybe we do want to put this into some data structure, like a map. So we want to take our lookup table and say, hey, what treat is allocated to marshmallow, or what treat is allocated to milkshake? Well, we want to essentially convert it into an unordered map or some other kind of hashing data structure, maybe. We could do this in C++23 using std ranges 2. Std ranges 2 says, take this range, which is potentially lazily generated, and stick it into a container, convert it into some container. So you could give this an unordered map, you could give this std vector, and it would give you a vector of pairs, a bunch of different things you could do here. Note that I'm not actually having to specify the key and value type of the unordered map. This will be deduced for me. This is quite handy, especially if there's a lot of machinery on top of this. Maybe you can't easily tell what the key and value types are, where you can just say unordered map, work it out. Okay, so we've now given our cats some treats. We've done some work, we've done some training with them so they weren't jealous. Maybe we want to do some more training with our cats. Maybe we want to, instead of just giving them food, we could offer them food and they have to give us their paw, and we shake their paw, and then they open their mouth and we give them a treat, and then maybe they make a mess, because my cats make a ton of mess when they're eating. How could we express this in code? Well, one way we could do this is something like this. We have our cat type down at the bottom, which has an offer food function. And this returns an optional paw. So maybe the cat, we gave the cat the food and the cat put out its paw. Or maybe the cat forgot that it was supposed to put out its paw, or got bored, or saw a mouse, or I don't know. There might be any number of reasons why it might not give us a paw. And then we shake the paw, and then maybe the cat wanders off because it saw something else out. All of these are returning an optional because they might not happen. The cat might not make a mess. It's kind of unlikely, but it might happen this time. So how do we then code up this function of feeding the cat, offering the food, and then if it offered us the paw, then shaking, and then if it offered us a mouth, so on? Well, we could just do it like this. We could say, offer the food, and then we maybe get a paw back. So we check if we did get a paw, and if we didn't, then we return null. And then we shake it, and maybe we got a mouth, so we check it, and if not, we return null. And you can see that the more and more steps we add to this, the more noisy it gets, the more code we have to write to just marshal this data around. Really, we just care about doing these steps. Like maybe we could format it like this. We could use the if initializers to do this work. Maybe you prefer this. We just do the offer food and check it in the same line. But again, the more of these things you add, the more it's going to shift horizontally. It's not going to be very pleasant. There's just a lot of noise here. We just want to say offer the food and then shake and then feed, and that's it. Well, in C++23, you can do pretty much exactly that. You can say offer food and then shake and then feed. This reads pretty naturally. Even if you maybe don't know C++, you can kind of work out what this is doing. So this is part of the new Monadic interface for std optional in C++23, which is actually a paper that I wrote. So I like this feature. This comes with a few things. There's and then, which allows you to compose functions which return optionals, just essentially crushing them together. And if at any point something returns null opt, then the whole thing is just going to return null opt, and the rest isn't going to happen. Then there's std optional transform, which allows you to change the value stored inside the optional as long as there is one. If there isn't, then it's just going to be null opt. And then finally, there's std optional or else, which lets you call a function if the optional was empty. So these are some helpers just to make dealing with optional a much nicer, cleaner, more ergonomic experience. But maybe we look at our code, we decide we don't have much information here, right? We said that a bunch of these things could fail for a variety of reasons, but we don't have that information in our code. We just get null opt. Oh, the cat didn't give us a paw. Why not? Null opt. Didn't make a mess. Why not? Null opt. So maybe we would like some information on why something failed. Well, C++ has something for this. It's called std expected. You might be familiar with this as like Rust, as the result type in Rust, or in a bunch of other languages have something very, very similar to this idea, or the either monad. It's the same kind of idea. Either we have the expected value, the mess, the mouth, the paw, or we have something representing the unexpected case, the error. So in this case, our error type is that representation of the error. It's going to give us some information about why this thing failed. We don't yet have the same monadic interface the optional is getting in C++23. There is a paper in flight. I don't know if it's going to make C++23, but hopefully at some point, std will have the same kind of interface that that std optional now has in C++23. But how would we implement expected? Say that we're implementing the standard library, or we're wanting to make some changes to std expected. We decide to write our own type. Well, let's look at maybe one function is the value. You want to get the value type out of this thing. But you also want to maintain the const ref qualifier of the wrapping expected object. You can maybe hear the washing machine in the other room just started. Unfortunate. So we have to write this 4 times. We have to write the const ref qualified version, the ref qualified version, const ref ref, ref ref. This is a lot of noise, kind of like my washing machine. This is my washing machine. You don't want to write this code for every single member function you have in your type, right? You're going to quadruplicate everything. It's easy to get wrong. It's hard to maintain. It's just not what you want to be doing. So C++23 gives you something for this. It's called deducing this. So this says, I don't have to overload these things anymore. I'm just going to deduce the const ref qualifiers of the explicit object parameter. This used to be the implicit object parameter that we don't see in the declaration. Now we see it in the declaration. This function takes a single parameter called self and is qualified with this keyword, which says this is special. This represents the object which you called this function on. So now if I call value on an R value, then it's going to be deduced. Self is going to be deduced to an R value. If I call it on an L value, it'll be deduced to an L value. So this gets rid of our quadruplication of code. It also solves some other things. This lets us do recursive lambdas, funnily enough, because we suddenly have access to self inside the function. It also lets us do CRTP, the curiously recurring template pattern, without having to template our type on the derived type, because self here can be a derived type. It doesn't necessarily have to be expected. Like if you derive something from expected, it could be deduced to that. So we would no longer, our CRTP would be a lot simpler. It also fixes a few other nooks and crannies of the language. I worked on this paper as well. I would recommend giving it a look, because there's a lot of things which kind of fall out of this design, which are not immediately obvious. This is maybe my favorite C++23 feature. I think this will clear up a lot of code, especially library code, if you have to write this kind of thing. Okay, so now our cats are pretty well trained. They've done a really good job. We want to give them a bunch of treats. So maybe we just want a treat generator, something which just generates us as many treats as we want, and we can just give them to the cats. Okay, so we have std generator. We have our treat generator, which we get from something we're calling make treat generator, which we'll see in a bit. And then anytime we want some treats, we just say, okay, well, this is an infinite range. This is an infinite range of treats. We're just going to take 10. You could use any kind of range adapter you like here. It's just a range. This is an infinite range of treats. We don't care where they come from. They're just there somehow. Std generator isn't yet voted into C++23. My understanding is it will be, but it's not there yet. But even if it doesn't make 23, there's a bunch of open source implementations, including one which I wrote, which you can use instead. So let's have a look at how this works, because this is an infinite range. Where are we getting these treats from? Well, one implementation of make treat generator could be we start off with some number of treats, say 50, and then we have an infinite loop. If the number of treats we have is 0, then we're going to go get some from the shop. And then regardless of whether we did that or not, we're going to decrement the number of treats and yield back a new treat to our caller. So this co-yield treat keyword, because our return type is a std generator, what this co-yield means is halt execution of this function, of this coroutine, because this is a coroutine, give the caller back this treat, and then later I can be resumed and we can go around this loop. So even though this looks like an infinite loop, which is never going to stop, our function isn't just going to loop forever and our program will never terminate. This function is going to suspend on the co-yield, and then when we ask it for another value, then it's going to go around the loop. So this will be the first standard library coroutine we would have. There are a bunch of different kinds of coroutines we could write, like tasks, shared tasks, whatever, but this will likely be the first one that we get. Okay, how do we get our cat object in the first place? Well, unfortunately, the API which I deal with for getting my cats is a very old, crufty C API. It looks something like this. We have a getCat function, which takes a pointer to a cat, and it will allocate a cat somewhere and then fill in this pointer, and it's an out parameter pointer, essentially. And you give it the color of the cat that you want, which is represented as an int, even though we have an enum for it in our nice C++ code. And then we have a deleter function, because we want to reclaim the memory for the cat once we're done with it. So how are we going to use this in our nice C++ 23 application? We don't want to forget to reclaim the memory. We don't want to be dealing with the int for the color when we've got nice enums, things like that. So we want to be using like a unique pointer for this, right? So maybe we'll create a type, which will be our cat deleter. And then we'll do something like this. We'll create a unique pointer with our cat deleter. But then in order to get our cat, we need to create a cat pointer, give it the address of that. We need to static cast our color to an int, and then we're going to reset the unique pointer to the raw pointer. You could potentially just construct the unique pointer instead of doing a reset, but maybe this unique pointer is a member function, and you can do this in the member initializer of the constructor. You'd have to call reset. And this gets even uglier if this wasn't just an out parameter, if this was an in-out parameter, and the C function had to look at the current state of the unique pointer in order to give you back the return value. You basically have to do this resetting. You have to manage the memory of the unique pointer, maybe release it. It's just kind of a mess. The static cast int, we need to be thinking about what type we're casting to. In this case, we look at the declaration for getCat and we see it as an int, but maybe we don't know what the underlying type of the enum is. There's a few things going on here. Static cast are just kind of nasty. So C++ 23 gives us some tools to help with both of these things. We now have std out pointer, which handles that resetting and everything for you. And there's also in out pointer, which is for that use case where it depends on the old value of the unique pointer. Then we have std2 underlying, which will take the enumerator and cast it to the integral value of the underlying type. We don't have to do static cast. We don't have to think about what type it is. We just say, give us the integral representation of this thing. So this, I think, is a much more ergonomic solution. A few things here which have cousins. Out pointer I already mentioned. In out pointer for determining if something's a scoped enum, we now have a type trait for that. And since we're using unique pointer here, can quickly mention that you can now use const expert unique pointers, which is very cool. On that note of unique pointers are, of course, move only. You cannot copy them. And this has a few knock-on effects for usability. Like, for instance, if we have a cat action, which is some action our cats might take, which gives us back some mess, and it has a name associated with it. What if our action here has to capture a unique pointer? Like this. Say we have a cat pointer, we have a cat action, and we have a lambda which captures this unique pointer. This does not compile because std function does not support move-only closures, and this closure is move-only by virtue of having a unique pointer as a member. So this isn't great. One way we can get around that in C++23 is using std move-only function. So this is very similar to std function. There's a few differences which you can look up, but the basic idea is that you can use this for move-only closures. Okay, so we've dealt with all our unique pointers and our CruftDC interface. Now we want to make something a bit nicer to use. Maybe we want to get a cat from a color. You know, I have 3 cats, as I mentioned. I have a black cat, a tortie, a ginger cat. I don't have a calico cat, or whatever other colors that you might put in this if it wasn't on a slide. But we want to give a nice interface for giving a color and getting back the correct cat. So one way we could implement this is we can use the using enum feature, which was C++17 or 20, I can't remember, a relatively recent feature, to say, okay, if it's black, return lexical cat. If it's ginger, return marshmallow. If it's a tortie, return milkshake, and otherwise use std unreachable. Std unreachable is if you're used to like built-in unreachable, which is a compiler intrinsic in a few compilers. It's the same thing but standardized. Basically says, hey, this is undefined behavior, and the optimizer can assume that this didn't happen, which in some cases can give you some nice performance improvements. Okay, so we've got a nicer cat from color implementation here. What other things do I do with my cats? Well, my cats like to sit in boxes. Right now, Marshmallow is here. He's not in a box. He is on top of the cat bed, which I bought him instead of inside it. But my cats like to sit in boxes, and I like to keep track of where the cats are. And so I have a big array of boxes. I then have a multi-dimensional span over my boxes. I don't think MD span is making C++23, but this is also something which is in the works and you can find open source implementations for. So I've got a bunch of boxes which might contain cats, and I have a multi-dimensional view over this single dimensional array. How do I index this thing? Well, in the past, maybe you used like a call operator, or you use 3 sets of square brackets, but in C++23, we can just have a single set of square brackets and just put commas inside them. We have a multi-dimensional indexing operator. This is nice. This is one of those like really small things which actually makes a quite nice usability improvement, I think. And maybe for whatever reason, if we wanted to make sure that we were saying these are size t's, we could use the new std size t, the new std size t literal. And I'm just seeing in my StreamYard chat that Daisy's saying the MD span is still on track to make 23. So that's good news. So, hey, there should be a star here for this being a C++23 feature. So that's great. Yeah, if you wanted to say that this was a size t, then you could use these new literals. Maybe it doesn't make sense in this case, but in other cases it might. So now that I've had all of these boxes, I want to track who's in boxes and which boxes they're in. So I have a little monitoring chip, which has some machine learning stuff, and then has a little display, and I can communicate with remotely. It's wonderful. And so a couple of functions in it are, of course, I have to collect this box data, which cats are in which box. I need to pack it into some format I can send over the network, and then I have to actually do that job of sending it. So in my dispatch box data function, something I could do is pack up my box data and then send it over the network. But I know that my specialized chip has a different byte order than the network, so I use this new std byte swap to just flip the bytes into the correct order. This might compile down to a single instruction on your processor. So maybe if you used to use intrinsics for this, you can now use the standardized version. Now, how do we pack our box data? Well, my chip has specialized hardware for doing this because I designed it myself, but I can't call it at compile time. I have a compiler intrinsic, but it's not const expert. So how do I deal with this? I still want to do the most efficient thing at runtime, but I might also want to do this thing at compile time if I have some box data that I know ahead of time that I want to send somewhere. So one way I could do that is using the new if const eval. So if const eval says if I'm being compiled at if I'm being run at compile time, we're going to do this thing. Otherwise, we're going to do this other thing. So up the top here, I have some more costly const expert friendly algorithm, and in my else branch, I have my compiler intrinsic. And maybe my implementation of if const eval might have it might use these new CMath functions, which are now said to be const expert friendly. Okay, but what if something goes wrong? Maybe something goes wrong and I want to display an error. I want to maybe display the stack trace or something on a little hardware display that I have next to my desk. So one way I could do this is my hardware has this function I can call to just get a display buffer. This is just a bit of memory mapped. It's some memory mapped I/O which I can just write into, and it will just appear on the little screen I have next to my desk. So one way I could use this, if result was false, then I'm going to get my display buffer, and I'm going to make an O-span stream of it. This is new in C++ 23. It's kind of like string stream, but it's for when you have already allocated backing storage that you'd like to use instead of dynamically allocating under the hood. Then if I want to write out the stack trace, I could use my new C++ 23 std stack trace. There's quite a fair bit of API surface area here, so you can go look at the documentation for this. But basically, this gives you the ability to get the current stack trace, to iterate through the frames, to print them out, things like that. Quite handy. My little chip also has some commands which you can issue over the network, and these need to be semicolon separated. So if I have a bunch of commands which I've already written, then I could semicolon separate them using the new std_views join with function to just take this range and join them all into a single thing with this delimiter. And then maybe I dispatch this over the network and I get back a string response. Something might have gone wrong. I know that something gone wrong if at any point in this string there is the word error. And what I can do now in C++ 23 is I can check if a string contains another string without having to do .find is not equal to string npos. So this is just one of those tiny things, but I'm sure you've had a bunch of times you're like, does this string contain something? How do I do this in C++? Oh, I use this nonsense. Now you can just say .contains. Makes much more sense. And finally, when my cats are about to go to bed, I like to get them to count sheep so that they sleep well. So I have a function which helps them count sheep. One way I could do this is I could create a vector of just 100 zeros. I could then make this vector count from 1 to 101 by using the new stdranges iota algorithm, which will just fill in 1 up to 100 in this vector. And then if I want them to get them to count this, I can just loop. While this isn't empty, we're going to shift the numbers to count left by 1 and get whatever we shifted off the end and count that. So stdranges shift left just takes the range and shifts it left the number of elements you tell it to. And then, as you might expect, there is also shift right. So that is now my cat to bed. This presentation is also getting to bed. So this is an outline of everything I talked about. I'm not going to read off this slide. That would be horrifically boring. But if you want to take a screenshot or anything, this is all of the features in C++23 which I mentioned in this talk. There are a few things which I didn't mention. Some which I think are interesting are ranges starts with and ends with for finding prefixes and suffixes. StdView slide, which gives you a sliding window view over a range. Adjacent and adjacent transform, which are the same, but the instead of a runtime size window, it's a compile time size window. Then there's std invoke r, which is like std invoke, but you can also give it a return type to convert the return to. And then there's a couple of type traits for working out if you're going to have a potentially dangling reference. There's a few other things which I didn't have time to cover and didn't want to put on this slide, so you can go back to that CPP reference thing if you really like, or Wikipedia or whatever your preferred source is. But I think these are most of the ones which are interesting to most users, I think. So thank you very much, and I hope that you enjoy using C++23. I'm gonna check for questions. I think we're pretty much on time, so if anyone has any questions, you can head over to Learn TV and stick them in there. And as soon as we dry up on those, then we're gonna move on to the next session. Yes, and now of course those topics are in this talk because I wrote them in. Yes, it's a comment saying now these topics are in the talk. So yeah, I guess so. I've got a question here. Are we settling for and then and not then in C++? Yeah, so this is an annoying naming thing. So you might have seen like std future got .then, but my recollection of .then for std future is it's not quite the same as and then. And then is essentially like just a monadic bind. I think .then for futures is somewhere between monadic bind and functor map, but I might be wrong on that point. But yeah, this was a whole thing. I'm sure you can imagine the bike shedding which goes on with this kind of thing. I'm getting confirmation from Daisy that yes, future.then is like between monadic bind and functor map. So yeah, that's why it's not the same name, because it's not quite the same thing. Okay, I'm not seeing any other questions, so I think that is